Come to the next one, parity. Parity, simply it means it's a mirror symmetry, exactly like a mirror symmetry. So in front of the mirror, if I raise my right hand, it will show left hand. So mirror symmetry. So another thing is this is coordinate reversal, right to left. So this is coordinate reversal, another name. So coordinates is reversed. Coordinates are reversed. So for example, if you have x, that will be minus x. If you have y, that will be minus y. Coordinates are reversed. So that's why it's called as coordinate reversal. So exactly like a mirror symmetry. So for example, if you take, if you are going to remove the lid cover of the bottle, So I will have to use only like this, right hand. Okay, right hand. If I want to close this one, left hand. Correct? So this is something like that. So the space reflection about the origin of the coordinate system is called the inversion or parity operation. So this is called a parity operation. So symmetry in reflection and inversion. It has a discrete, this we discussed already, it has a discrete unitary transformation. This symmetry involves replacing every particle interaction and decays with a mirror image counterpart. So they thought earlier, that whatever happens in front of the mirror, the same physical quantity also can be observed inside. So they thought. The parity transformation consists of an inversion or reflection through the origin of the coordinate system. For example, you have a system like this. So x, y, z. So you have a mirror. The mirror image of this one will be exactly like this. Okay. For example, this is just a rough idea. You have a mirror like this. The z will not change. Correct. In the mirror, this direction, this z will not change. So that's why I said it's a rough idea. Whereas your y will be changed into minus y. See this direction. So this goes towards this direction from left to right. But here right to left. What of this x? X towards u. But here x goes inside. Correct. But is it it should be exactly like this. Correct, in the mirror. But is it just in the opposite direction? That's why I said it's a rough idea. So mirror image. So transformation from one coordinate system into another coordinate system, we call this as a coordinate reversal. Of course, we know z coordinate will not change. This z coordinate in front of the mirror, z coordinate will not change. Only this alone will be changing. This side to that side to this side. So that's why we call this as coordinate reversal. So under parity operation, parity transformation, x, y, z one coordinate system into another coordinate system, minus x, minus y, minus z. Okay, so this is just an idea. So put together that will give you r equals xi plus yj plus zk. So you will have r coordinate system under the parity operation will give you minus r. Okay. Now we call, so suppose we take velocity dr by dt, r will change into minus r. So that's why we have written minus dr by dt. So this is a vector quantity. Vector quantity alone will change. If you think, then what is the scalar quantity? The scalar quantity remains the same. So what we call this is ordinary scalar. Okay. Now look at this one, m into dr by dt. So mv, momentum. R changes into minus r. M will not change. Correct. M will not change. Under parity, m remains the same. Vector quantity alone changes here. Correct. Vector quantity alone changes here. I should not say, but however, we will see. So m dr by dt gives you minus m dr by dt. So this is called a momentum. So momentum will change. Momentum is a vector quantity. Now what about this one? L is a vector quantity. R is a vector quantity. P is also a vector quantity. R will change into minus r, as we said just now. P will change into minus p. What are minus into minus? Plus. So this is also a vector quantity, but minus sign, what are the minus sign? Doesn't change. We call this as a pseudo vector. So these are all real vectors, ordinary vectors. Sometimes we call this as polar vectors. Is it okay? We need not think always that vectors alone will change the minus sign, scalars will not change. No. In some other cases, like exactly like L equals R cross P, in this case it doesn't change the sign. See, it doesn't change the sign. With the parity operator, with the mirror image, doesn't change the sign. So what we call this as pseudo vector, axial vector. What if the spin? The spin also will never change. See, spin doesn't change. It's a pseudo vector. It's a vector quantity, pseudo vector. And L plus S, that's a complete one. L plus S will give you J, correct? L plus S. So that also parity operator, that also will be your, it's a condition for the parity operator. It's a transformation. So this also pseudo vector. So J after the transformation will give you the same J. So pseudo vector. Real vector will change the sign. Pseudo vector will not change the sign. The real scalar will not change the sign. Pseudo scalar will change the sign. Is it okay? So these are all examples, few examples for your parity transformation. And this parity transformation, we can have a small look one idea. Before 1956, people thought that the physical laws are invariant under parity. So whatever that happens in the physical system, the same thing also will happen in front of the mirror. They thought like that before 1956. And Lee and Young, they predicted that parity symmetry will be broken for a weak interaction. So there will be a strong interaction as well for a weak interaction. Some interaction will be there, especially for the decay elements, radioactive elements. They thought that, Lee and Young, they predicted that the parity symmetry will not occur, will be broken for a weak interaction. Weak interaction means emission of electrons, which is nothing but beta decay. So beta decay is called as weak interaction. For example, just take cobalt 60. Just take cobalt 60 atoms. So they imagine, okay, they predicted that for the weak interaction, the parity symmetry is broken. So that was the prediction predicted by Lee and Young. Just take cobalt atom, cobalt 60. It's a radioactive element. Just to cool it to a lower temperature. So the moment of electrons will be very less, almost zero. Now you apply magnetic field. The moment when you are going to apply the magnetic field, the spin will be aligned together in the Z direction. Okay. Suppose we consider the moment of the electron, that spin of the electron is like this. Okay, like this. The direction of spin will be exactly towards up. Okay. See here. If it is the moment of the spin of the electron is exactly like this, then the direction of the magnetic moment of the spin will be exactly towards up. So it shows like this. And they observed that's actually it was done by a lady, Wu. They predicted, but this experiment was carried out by Wu. So Wu was a lady who did this experiment. That is cobalt 60. She cooled the cobalt 60, very low temperature, applied a magnetic field. So she observed that this is the application of the magnetic field in the Z direction. Okay. Now just look at the spin. Spin will be there. It's aligned. Okay. The magnetic moment of the spin exactly aligned with the external magnetic field. And she observed that she had some detector. She observed that the emission of electrons where it occurs the most. She has kept the detector here. She has kept the detector here. She kept the detector here. Here she observed, and she could find out that all the electrons, the most of the electrons which are coming out exactly in the opposite direction of the Z. Suppose if it is Z, then minus Z, she could find out most of the electrons which are coming out. That is, beta decay occurs exactly in the opposite direction. This is what she observed. Suppose if we have any mirror image, it should be the same, correct? Under parity transformation, it should exactly resemble with a mirror image. So this is a rough idea. We'll understand first, then after that we'll go through detail. First we'll have a mirror image. If it is so like this in the mirror, it has to show down, correct? Because it has to show down, because this spin, see here you have a spin, but in the mirror it will be like this. If it is shows this direction, the magnetic moment of the spin will be downwards, correct? Here it is upward. So magnetic moment will be for the spin, it will be downwards. What is the direction of the electron which are coming out, beta decay? It will be exactly like this. Does it resemble exactly the same, the mirror image? No, it is not a mirror image. So one goes like this and another one goes exactly like this. correct? But actually what happens, you have this is your uh, what is this one? This is your spin. So thus now we looked into the spin is a pseudo vector, correct? So because S doesn't change the sign, so it's a pseudo vector. What is the momentum? Momentum already we looked into. This is ordinary vector. So momentum will change the sign, spin will not change the sign. So they concluded that spin will never change. See, this is your direction of the spin. So this is your direction of the spin. So spin will never change the sign. What is the momentum? Momentum will change the sign. So that's why momentum exactly in the opposite direction. See, but this is the application of the magnetic field. The occurrence of electrons which are coming out in the opposite direction. Correct? Opposite direction. You just resemble with a mathematical idea, exactly they are same. So this is exactly now mirror image. See, mirror image of this. So that's why they conclude that for the weak interaction, it fails. The parity doesn't work. Parity is violated. Parity is violated. Just they concluded. So before 1956, they thought that parity was accepted. But after this invention by Li, Yang and Wu, they thought that parity has been violated. So parity did not work here after 1956, for which these two persons got Nobel Prize. Wu did not get Nobel Prize. So I don't know why. What is the reason? So Li and Yang got Nobel Prize. So parity in the year 1957. Okay, parity symmetry is violated in weak interaction. So this is the example. So spin of cobalt 60 and beta decayed electrons are in the opposite directions. As I said, opposite directions. Mirror image will be spin of the cobalt 60 and the beta decayed electrons are in the same direction. See, they are in the same directions, which is not possible to observe in nature. Which is not possible. So that's why we say that in most of the cases, especially beta decay, parity is violated. So this is a definition for a parity. Parity operator operates on the wave function that will give you this psi minus r. So r becomes minus r. What we call this as even parity. Suppose minus is there, we call this as odd parity. So we have even parity and odd parity. If you are going to operate twice, then this minus will become again plus. Okay, you are going to operate twice. For example, p squared psi of r will give you plus psi. Okay, the parity operator is a Hermitian operator. So p dagger will be your p. P squared is equal to unit operator. The parity operator is unitary. Since its Hermitian adjoint is equal to the inverse, so as we just now discussed, u dagger equals u inverse, correct? So similarly, p dagger equals p inverse, and p squared will be equal to 1. That is unitary operator. The eigenvalues of p squared will be plus or minus 1. Very important one more question. Eigenvalue of the operator, parity operator will give you plus 1 and minus 1. Plus 1 or minus 1. The eigenstate psi plus is said to be even, psi minus is said to be odd. Therefore, the eigenfunctions of the parity operator have definite parity. They have either even or odd. And parity operator will commute with Hamiltonian because it's a symmetry. It's a conserved quantity that will show constant of motion. So then the parity is conserved. Then we can say a constant of motion. Further, the parity and the Hamiltonian will have simultaneous eigenstates. If they commute, they will have simultaneous eigenstates. The last two title will be time reversal. Okay. So time reversal, we are going to have some operation on a particular time. We are going to reverse the time. For example, t becomes minus t. We are going to reverse the time. According to the symmetry, even in which the time runs backward or all the motions are reversed. Okay. Another time reversal. So this is time reversal operator. So your wave function, time reversal operator will operate on wave function. So that is termed as exactly like this. The t alone will become minus t. So t will become minus t. Okay. So definition. This is a definition for your time reversal. So for using your Schrodinger wave equation, time reversal operator operates on Schrodinger wave equation will give us exactly like this. So t will become minus t. So t will become minus t. Correct? Your t will become minus t. T will become minus t. Also, psi will become your psi star. You will have to take the complex conjugate. Okay? So psi will become your psi star and t will become your minus t. Okay? So this is for the time reversal definition. For example, Schrodinger equation is given by this. You are going to use the time reversal operator. First use the time reversal operator. So we are going to prove this one where we have done both operations. One is t becomes minus t. Then another one is you have taken the complex conjugate. When you use the time reversal operator. Okay, we will check. So this is your eigenvalue equation, Schrodinger wave equation, time development equation. Just take the time reversal operator for this. You will get t becomes minus t. T becomes minus t. So we will get, correct? So this will become your minus I h cross d by dt psi of rt h psi of rt. Okay? Is it okay? Minus I have taken here. You just compare these two equations whether they have same solution or not. You just compare this one. This is a solution, psi of rt solution. But here it is plus sign, here it is minus sign. So they will not have a same solution, correct? Suppose if you take a complex conjugate of this, just take the complex conjugate. Taking the complex conjugate will give you I h cross d psi star r comma minus t, then that will give you the same factor. Now we will have the same solution. So for the time reversal operator, we will have to take the time t with minus sign, as well we will have to take the complex conjugate. Only then we will get the same answer. So it is the same as that of taking the complex conjugate of original function like this. It's a solution of Schrodinger equation. Okay. So now you can get back the same wave function. Okay. So this is the answer. We are going to take the complex conjugate. Taking the complex conjugate will give you both the terms will be equal. So it implies that a physical system in which the behavior at time t and time minus t are the same. Thus the time reversal is a balanced symmetry. So time reversal is a balanced symmetry. So we can say that t comma h which is equal to 0. T is a symmetry. T comma h, commutator bracket, t comma h equals 0. Both will commute with each other provided t is symmetry. It's a conserved quantity, we can say. So thus the time reversal is the balanced symmetry of the Schrodinger equation, and the time reversal is the complex conjugate operator and the antilinear. Antilinear means you are going to take the complex conjugate. Okay, C1 becomes C1 star, C1 psi for example, then you are going to take the complex conjugate, so C1 star it becomes. See, this is the definition for your time reversal operator. T operates on the wave function will give you, so not only minus t but also the complex conjugate. So definition for your time reversal operator. So what are the properties? So 4 properties are there. We will see one by one. The time reversal is an anti-unitary operator. So it has both unitary as well antilinear properties. Anti-unitary operator means this will have unitary as well antilinear properties. Unitary means the inner product of two states remain the same, preserved. Unitary means the inner product before and after the transformation will be always constant, preserved. Antilinear means you are going to take the complex conjugate. Okay. For example, the first one, the unitary operator before and after. The norm before and after. So they are the same. So norms are preserved. Norm is preserved. You are going to take the transformation. This is the old one. This is a new system. Tilde is the new system. T psi act, that will give you psi tilde. Tilde is a new system. Time reversal operator operates on the any quantum system will give you tilde, that psi system. Okay, the quantum system of the new system that we call this as tilde. So norm is preserved. Now for the antilinear property, here it is defined as the time reversal operator operates on this one will give you the complex conjugate. See, complex conjugate of these two numbers. So these two conjugates. So Ti will give you minus Iti. So as I said earlier, the commutator T comma H equals 0. It implies that T is a symmetric quantity. Conserved one, both will have simultaneous eigenstates. So TH equals HT. So T commutes with the Hamiltonian. Eigenvectors of the same time reversal operator are also eigenvectors of the Hamiltonian. The last one will be the commutation relations with the time reversal. The coordinates will never change. TR equals RT. The time reversal operator operates on R will give you R and T. So this one will never change. So what we call this as even function. Momentum with a minus sign, it will change with a minus sign. Spin also will change into the minus sign. Angular momentum also will change into the minus sign. So they are all called odd functions, and this one is called an even function. So this is about symmetries. So we learnt so far symmetries and the conservation laws. The next one will be unitary transformation, and third one we learnt about the parity, and the last one time reversal and time reversal some properties. Okay, so thank you students. So that is the end of the third unit. Okay, bye. Let us see.